All right, welcome everybody to the Sherpa tutorial. This will be a different tutorial than we had so far, and we have not much time to cover everything. But I start with the links to our Sherpa pages and GitHub pages here in the first slide. And I'd like to say that this is our core team, and Doug and Moritz joining us for the tutorial today. And Nick is also online to help with any installation questions. We did circulate the Google poll, and we had 20 responses. And based on these responses, we know that half of the people used Sherpa and half of the attendants did not. So we have a range of users. Here we also asked how, where's my down? What type of analysis people performed. So a lot of you perform 1D fitting, and the other types of analysis in Sherpa were also performed. So the most important part of the tutorial was, what do you want to learn about Sherpa? This is the question which was answered by all of you. And we decided to have these breakout rooms and cover all these topics below, plus the details of these general capabilities, which will be covered also in the notebooks. We have several notebooks, and I hope, Doug, can you put the link into the chat to the notebooks which were prepared for the tutorials? And as you can see, we have different topics by different people. All of us will cover the basics, and we will answer questions if you have any questions. And I will focus on Bayesian analysis and statistics. Doug will cover general questions related to spectral fitting, Python issues, etc. Also 2D fitting. Moritz can answer any questions related to pile-up modeling, spectral analysis, etc. So we'll also have some specific questions which are displayed here, and those are covered by our notebooks available online. I note that there is this one specific question about comparison between Sherpa and XSpec, and we are not going to go into details. This has been covered to some extent by BXA tutorials, where you saw different interfaces in XSpec and Sherpa to BXA and different functionality. The questions related to plotting and seeing model components will be also addressed in notebooks and by talking to Doug. So we will split into the break rooms. I stopped sharing this, and I don't know if people want to see this previous page, and then I stop. But everybody who asked the questions know what name is listed there, so we'll go to breakout rooms. I Google page. So this is our GitHub page with Sherpa notebooks, and as you can see, we have how to do data, how to make nice plots, how to split models, how to do simple image analysis. These are the notebooks. I will start with this Bayes uncertainty test notebook, which I have here. I already started. So this basically shows the Bayesian modeling you can do with Sherpa. And this is the implementation, which is based on 3 papers, which were published. Our first paper was on the standard Bayesian concepts and what to do with X-rays when you want to do analysis in Sherpa. And this also shows this posterior simulations. The next 2 papers describe the usage of the Bayesian analysis to include uncertainties on calibration, which can be extended to model uncertainties, which you can use. So the notebook was run with Java 4.13, and Java 4.13 contains Sherpa and Jupyter notebooks, and you can start with importing basically Sherpa Astro UI part into your environment. This is notebook environment, and then you can set up statistics. In this case, I use just Poisson likelihood defined as cache, and our optimization method, in this case, is Neldermeet. Sherpa has 3 old style optimization methods, which are based on gradient approach. So you do the minimization using the gradient optimization. So simplex, this is the Neldermeet algorithm in Sherpa, is used here. We also have standard Levenberg-Marquardt algorithm and Moncar, which is differential evolution, which is more complicated than just standard Monte Carlo method. So we're loading the Sherpa, data into Sherpa with this load data command. We can ignore the range and then set up model parameters. In Sherpa, you have to name the model components, as was also noted at BXA. We can then just run fit with fit commands. You get the output. You have also information about optimization and likelihood. Here we've got the log likelihood output. Actually, this is likelihood, it's not log. And then number of data points and degrees of freedom. And we need to use the covariance matrix as an input for the initial scales to MCMC runs. And this is the covar function in Sherpa. And we do the plot fit. We have plot fit residuals. There is several options one can do. So in order to run MCMC and Bayesian analysis in Sherpa, you have to select your sampler. And we have basically Metropolis Hastings sampler. So there are 2 types, Metropolis Hastings and Metropolis Hastings. So there are 2 ways. So it's Metropolis MH and MH. We have also this additional Prague-based and full-based samplers, which relate to the calibration uncertainties, which I will show later. So you select your sample. We just select Metropolis with Metropolis Hastings. And when you get sampler, you have all these options, which you see. You can change the priors. Our default priors is basically the uniform prior, and true means that this will be used in it, and original scale for all the parameters is also true. And there is additional scale parameter here, which sort of redefines the width of the function, which is used in the Metropolis Hastings steps. So depending on the scale, it could be larger jumping and narrower jumping rules. And then there is P_m is the fraction of the draws which are used via Metropolis and then Metropolis Hastings, so depending on the algorithm. So the main function which runs this analysis is get draws function. So you can get a help in Sherpa when you do help bracket get draws, and you see the function parameters here, arguments, and then it runs this. When you run it, okay, this is the call which allows you to run, and we usually have stats accept params, which is these are the arrays which will be called stats accept and params, and the array stats means you've got your statistic values out, accepted or not accepted draws, and then a range of parameters, so array of parameter values which were drawn. Then when you run it, you see that the flat priors, default priors were used. And when you finish running, which I'm not running it here, I mean, it will take a long time. I change, I set up the number of iterations to 1000, which actually could be run, but you can change the number of iterations. When you return, when it finishes, you get the race or draws, and you can check the best fit parameter values by basically looking at the arrays of the parameters and the minimum of the statistics. So you get the parameters with the which are the best parameters for the minimum statistics in this arrays, and then the standard deviations here, which were calculated based on those. You can visualize the entire MCMC run. So plot trace in Sherpa will just plot your arrays. And when I say plot trace stats, it basically displays the changes in the statistics values run across. Note that I started from the best fit parameter value. That's one of the things which we do in Sherpa. You pre-fit your data with the defined models, so you are close, and then you can use this MCMC to sample and check the parameter space and shape of the parameter space. So trace shows you that the statistics was jumping around. So we had the draws from different parts of the parameter space, and then plot trace on each parameter will display you the changes to these parameters with each iteration. You can also look at the two parameters, and within the scattered plot, you see how this parameters behaves, and you can see the correlations between parameter 0 and parameter 1, which is absorption versus photon index here. And then plot PDF will provide you with the default histogram distribution, and plot CDF will give you the cumulative distribution of that parameter. So in this case, it was gamma parameter, and you can get the median upper and lower bound just from that, and the same best fit. So to change priors, you can use any Sherpa function, and in this case, I use the Sherpa normalized Gaussian function to set up a prior for my photon index. And this is, so I have to define this function first and the parameters for that function. And then I modify the sampler. So here I change the default prior to false because I will need to apply this function to the parameters. And then the prior shape, which means it won't be different for this first parameter and the last, but it will be true. So I will set the Gaussian for the second parameter, and all parameters are on original scale, so I don't change that to log or something else. And I rerun my sampler with this new prior, and you can see that now photon index prior is listed here, and it's on it's this. And plot trace and scatter plots show again similar correlations. It's slightly different. You can notice that the shapes maybe of the trace of photon index is slightly different here and there. And I just show you how to plot just part of the arrays here. And the best fit again is shown below, but you can note that this prior changed slightly the parameter, photon index parameter. It's slightly different. It's still within the 1 sigma, so it basically reflects the change in the prior mainly, but it's all within the shape. So if you want to take calibration uncertainties into account, I show this here, but the main issue you have is to find the actual calibration data which you could use here. So this is concept, and this is all test. It's not a way you will actually do this because we don't have the calibration files. But this first loop shows you the standard way you run MCMC. So you have your data and your model, your prior, and then you draw parameters from that prior. And then you have on the other side, you have data and calibration of your data, and you compute the likelihood, and then there is a rule of accepting or not, and you update the parameter and you go. If you have calibration uncertainties, so it means that, for example, that your ARF behaves in, it is changes to your ARF are actually the ARF is the product which is also measured. So if you have an ARF, you usually assume that that's the best calibration you got. But there is uncertainty on how we measure the components of the ARF. So to include those into your analysis, you would include this calibration data in the loop. So you don't assume that you just have this as part of your standard convolution. You just have this at each step. You draw the data. You also you draw the model. You also draw calibration file here, and then you compute the likelihood. And you accept or reject. You can draw calibration file, and you can accept in certain cases in full base. You can actually improve your calibration data itself. So anyway, to do this in Sherpa, you change the sampler to Burke based, and then you can see that these options in the sampler contain two additional options. SimArf will be this calibration file of data, and then subiterations, there is a parameter which tells you how many subiterations you will do before you change the ARF. And I set the options here to my file, which is just the test file, and I changed the subiteration to file, and then to 5, and then you get this here. And this is my model as it was. And when I run, this is stat_sim. So not stat, but I make sure that I have arrays which are related to the simulations, and then I run and get the results. So I can compare now the results from the standard. This is the orange one from my standard Bayesian analysis with the narrow. Actually, this was the Gaussian prior, to the one where I was including calibration uncertainties. So you can see that in this case, the change in the posterior density on this photon index parameter is quite large. So including this uncertainties may impact your uncertainty on this parameter. And then plot scatter show the same. However, of course, this is just the test case. So I'm also showing the full base, which is described in this 2014 paper. And the full base allows you to also include the changes on the sigma of one more component. And I use the same files. This takes a long time to run. That's why I didn't run. But it's in this plot, you can see the comparison between the this orange one is the first Bayesian one. The green one is the one with the Burke base, and the blue one is the full base. So in the full base case, you basically improve the knowledge of your calibration. So from Burke base, you just sample whatever we know about ARF, and here we sort of improve and select the ones which better fit our data. So we get the change in the shape of the posterior, which is not so huge, but it's more accurate in that way. So to do the corner plots, which everybody likes, we import corner, which is a Python package from Dan Forman-Mackey. It's freely available on internet. So on GitHub, we basically get that corner package, and I set up my parvals arrays here, and then you just have to put them in the corner function, and you get this 3 standard default plots. there are many options in a corner plot, but this is this is one which highlights our best fit parameters and shows the histogram between this. And I didn't do this nice things. So that's the end of the Bayesian one. Are there any questions? No, I don't hear any questions.
If you have any questions, you can unmute yourself or you can raise your hand.
Yeah. Okay, well, so I have another one, let's see, another, where is it? Notebook, which is the model comparison via PPP checking, so posterior predictive parameter checking, that's what it is. So this morning we've heard about prior checks and posterior checks. So there are two different things, and prior is just checking the shape of your prior and how it fits to the data. Posterior checking will actually allows you to evaluate the model and maybe discriminate between the models. So here I have a notebook where I show how to do this in Sherpa. We have a function called plot_p-value, and that function does simulations, which I describe here, and comes out with the selection of the p-value for your model, more complex model. So again, you input your data and set up the statistics, and then you set up the model, you fit the data, and in this case, you add another component to the data to see whether power law or power law with Gaussian is a better model. And I fit this more complex model with additional Gaussian here, and this is the result. And fit residuals, this is just to show you the residuals here. So this runs a long time because I think our absorption parameter just goes all over the place, but p-value runs the simulations, and it assumes that we've got the best fit parameters for this power law model, and this is our null model, and we will test for the additional of the Gaussian line there. So you fit you simulate the data with the null model. You fit this simulated data with the null and with alternative model and calculate the likelihood ratio and plot the resulting distributions. And in this case, you mark the observed likelihood ratio and the simulations will be printed to the screen. So in this function, we do run the sampler. So it's running likelihood ratio and the Walker, assuming the multi-normal distributions, and you plot this later. So after I run this, it goes for a long time. At the end, what you see, and actually normally it doesn't print a lot information to the screen. However, in this case, we had this absorption, probing the absorption parameter, which goes outside the boundary, and we had all this warning. So there was a lot of rejections, basically, of this draws. So where you get to the end, what you see is likelihood ratio. So you have likelihood for null statistics, so for fitting your model with the power law, your data with the power law model, and alternative statistics, which is fitting your data with the power law plus line, or power law plus line, some other feature. And then the likelihood ratio, which is the one you observed. So basically one minus the other. And then the p-value, which comes from these simulations. So this is based on the display. Display is here. So the blue line is basically the outcome of the simulations, which is the ratio of the likelihoods in the simulations. And then the orange line is the one which we observed, which is 2.73. And as you can see, this p-value is based on the number of this, on the tail of this distribution, and it's 0.1, so about 10% of the simulated values were out of this. So in this case, the observed data are on the edge. I wouldn't say that this is a strong evidence for the line, and we probably would reject it because it's 0.1. I would accept if there was a 0.01 value, so this line would be somewhere far away. And you do this because typically the likelihood ratio test for this data is not well calibrated. So you run the simulations to calibrate and get this distribution in order to understand whether or not your likelihood ratio behaves the way you expect. Typically, you compare this to chi-square distributions, which our data and our model doesn't follow. So anyway, you can then also obtain the arrays with get p-value results. You obtain the arrays, and I just print part of this arrays here. So the samples, which will be part of this result object, you can do this array, and you can see what was sampling and what parameter values were sampled, and then the statistics for null and alternative models, and the arrays for the ratios. So there are only 10 I print, but I think we simulated 1,000. Yeah, there were 1,000 simulations, which was a lot and took a lot of time. One note that you have to do a lot of simulations in order to get your p-value right, because as you know, it's based on number of simulations, and you have 10 simulations, the p-value, you can have just one, right? I mean, would not tell you much. You have to run probably 1,000 or more, depending on the on what p-value do you want to obtain. So that so this is our GitHub site. We have currently these notebooks there, and you can you can go. So I was showing Bayes uncertainty and what was it? I thought that Doug, let me read one, because I put my, oh yeah, there it is, model selection. So that's the new one, just uploaded. So we have this, and this page will evolve. What I need to show you as well is our documentation. So this is our read the docs page, and here there is so there are installation and more detailed description of everything, and there are notebooks. So there is like quick start Sherpa notebook, and there is the description of what's in the notebook. We probably will add more notebooks in the future, but if you go to Monte Carlo and Poisson, you get the examples, and there is a 2D example which I didn't show, but there is a 2D modeling here and chains and all the details you can see. So you can use the Sherpa read the docs documentation, which also sort of shows the functionality which is independent of CHAO. And of course we have CHAO pages, which I don't think I have. Maybe this is page, no. When I go to Sherpa, so these are our CHAO pages, and we have where is our analysis documentation here, analysis threads. So we have a lot of threads here, and in fitting you have many, so you can follow. This is updated Bayesian analysis also with different focus in the description. So we do have a lot of documentation, and this is this is the software which has been matured over the years. So it's if you have questions, you ask questions via our help desk, you can go on a GitHub page and set up, send the issues to us, and we answer those as well. So also GitHub development means, the open development means that we can accept contributions from people. And as we could see, there is a lot of new people who want to do things. So if somebody has some ideas of what they want to do with Sherpa and extend Sherpa, then it will be great. They can contribute right away. Or tell us, or better yet, send us the prototype code or good code via GitHub.